Hello everyone, this session is based on Le Chatelier's principle and its applications. So what does Le Chatelier's principle say? It says that if we have a system at equilibrium, what is equilibrium? A reaction system where the rate of forward reaction is equal to rate of backward reaction, and it goes without saying if we have the forward and the backward reactions happening, the system has to be a reversible process. So a system which is at equilibrium, if it is subjected to a change either in concentration of the reactants or products, or a change in pressure, or a change in temperature, or even addition of an inert gas takes place, then this system is going to oppose the change. And since the equilibrium is disturbed now, it was at equilibrium to begin with these external changes being imposed on the system is no more at equilibrium, but it will respond in such a way so as to undo or neutralize or counter the effect of the change so that it will regain the state of equilibrium. So, in a nutshell, what is Chatelier's principle saying? That whatever change you are imposing on the system is going to move either in the forward or in the backward direction, but that direction should counter the change that you have imposed on the system. So, effect of changing concentration on a given reaction system which is at equilibrium. H2 plus I2 gives 2HI. So, I have taken different conditions quickly. If H2 concentration is increased, so what is the response of the system? To decrease H2. How will H2 decrease? If it is consumed. So, reaction shift will take place in the forward direction. If H2 is decreased, system will try to increase H2. Increase H2 how? It will be produced in this direction, that is the backward direction would be favored. If HI, that is the product, concentration is increased, how will the system undo the change? By decreasing the concentration of the product or HI, and that will happen if this is used up by moving in the backward direction. If we decrease the concentration of HI, the system will try to undo that change by increasing the concentration. It has to oppose the change imposed on the system, increasing, and this will increase when the reaction system shifts its equilibrium in the forward direction. So as a generalization, we can say that any reactant concentration, if it is increased, system will try to decrease it by consuming the reactant, and that will happen in the forward direction. If reactant concentration is decreased, system will try to increase the concentration by moving in the backward direction. And as a generalization for any product, if the concentration of the product is increased, system will try to use up that increased concentration by consuming that increased amount by moving in the backward direction. If the concentration of the product is decreased, system will try to undo the change by increasing the concentration of the product. And how will that happen? That will happen if more of the product is produced in the forward direction. Before we go on to study the impacts of other factors on an equilibrium system, let us understand why are we studying Le Chatelier's principle. So, or where are we going to apply Le Chatelier's principle? So, as an example, we have the we have the Haber's process, which is used in the manufacture of ammonia. So, once over here you have understood that if we want the reaction to move in the forward direction, I may either increase the concentration of the reactant or I may decrease the concentration of the product. So you can see that by understanding the movement of the equilibrium, which is the changes which aid in the forward direction, we can determine those conditions of concentration we've already studied, and we shall be studying of temperature or pressure, which will help us to move the equilibrium shift in the forward direction, which will aid us in getting a higher yield of the product which is being manufactured. So simply, Le Chatelier principle is helping us to understand what conditions of temperature, pressure, concentration are allowing us to improve the yield of a given substance which is being manufactured. Let us now understand the effect of pressure changes on a given reaction system at equilibrium. So let us increase the pressure of a system. So I have here, just to understand, this is a container having a gas cylinder. Let's say this is a piston I have, and that piston is a movable piston which we can increase or decrease the pressure. So if I increase the pressure, means I'm pressing it down. If I increase the pressure, the volume will decrease. We are already familiar that pressure and volume are inversely related. So if I increase the pressure, the volume will become less. As soon as the volume becomes less, the number of moles of the reactants and products will have lesser space. So per unit volume of the container, the number of moles will increase because they are crowded now. And how will the system respond? The reaction will respond to decrease the number of moles. That is, it's going to oppose the change. How was the change? What was the change? Increasing in the number of moles. The system equilibrium will shift in that direction, which will result in decrease of moles. Now, which is that direction? That depends on the type of reaction we are studying. But as a generalization, we know the system moles increased, system will try to undo the change by decreasing moles, and therefore that direction of the reaction will be favored where the number of moles decreases. Now let's decrease the pressure. If we decrease the pressure, then the volume increases. When the volume will increase, the moles will have more space to move around in the increased volume. That is, per unit volume, the number of moles decreases. How is the system going to undo that change? By increasing the moles. That means the equilibrium shift will happen in that direction where the number of moles is increasing. And just to easily remember, whatever happens to the pressure, the same thing is reflected in the number of moles. So if pressure increased, moles increased, system will try to decrease the moles. If pressure decreased, moles also decrease, system will try to increase the moles. So first case, here we just studied tries to decrease or increase. But what is that increase or decrease direction? That will depend on the nature of the reaction. So first type of reaction where the number of gaseous product moles is equal to the number of moles of gaseous reactants. This is the example, H2I2 giving you 2HI. 2 moles on either side. There is no impact of changing pressure on such a reaction system at equilibrium, because as long as the number of moles in both directions is same, the equilibrium is not disturbed, and therefore no impact of changing pressure on such a system. The other type of reactions are where the number of moles of gaseous reactants is greater than the number of moles of gaseous products. This is an example here we have. So, reactant 4 moles, products 2 moles. If we increase the pressure, inverse happens to the volume, that is, the volume will decrease, and volume decreases. I told you, pressure increases, the same thing happens to the moles. Pressure increases, moles increase, system will try to undo the change. Undo is the key word. We'll try to undo the change by decreasing the moles. Now with reference to our reaction, in which direction is the number of moles decreasing? In this direction, that is the forward direction. So for this situation, the response of the system will be to shift the equilibrium in the favor of the forward direction. Now let's decrease the pressure of the system. Pressure decreases, volume increases, more space for the moles to move around. So population decreases, that means moles per unit volume decreases. Also remember, whatever happens to the pressure, the same thing happens to the moles. Pressure decreased, moles decreases, system will try to undo the change. How? By increasing the number of moles. Now we need to see in our system, where's the number of moles increasing? Here 4, here 2. So the reaction shift will happen in this direction, which happens to be the backward direction, in order to increase the moles. The third case is where the number of gaseous products is greater than the number of gaseous reactants. So products are 2, the reactant is 1. PCl5 dissociating to give PCl3 plus Cl2. Pressure increase, inverse, volume decreases. Whatever happens to pressure happens to moles. Increased, increase. System will try to undo the increase in moles by moving in that direction where the moles decrease, which in this case is the backward direction. So equilibrium shift will be taking place in the backward direction. Pressure decreases, volume increased. If volume increases, number of moles per unit volume decreases. Also remember directly, pressure decreases, moles decrease, and the system is going to undo this impact. How? By trying to increase the moles. In which directions are the moles increasing? The moles are increasing in the forward direction, and therefore the system will try to regain equilibrium by shifting in the forward direction till the number of moles attains the same status as was present at equilibrium point. Now let's study the effect of change of temperature. So let's increase the temperature of a given system. If temperature increases, that means heat content in the container increases. System is going to try to undo the change by reducing the heat. The change we are imposing, but the response is by the system only. So how will the system respond? By consuming that heat. And how will that happen? When the system moves in that direction where the heat is being absorbed by the system, that is the endothermic direction. Let's decrease the temperature of the system. We're decreasing means we're cooling the system. So system wants to come back to the warmer or the at the status where there was more heat in the system, and that will happen if the system liberates or produces heat. And what are such like reactions called where heat is liberated? Exothermic reactions. So the system is going to move in the exothermic direction to increase the heat content when we decreased the temperature. And the system will try to absorb or utilize the heat to decrease the heat when externally the temperature was raised of the system. Please do remember, there's a very important point that in a reversible reaction, if the forward reaction is endothermic, the backward will be exothermic, or the vice versa is going to be true. So we have the Haber's process again, N2 plus 3H2 giving 2NH3 plus even this much heat is liberated. That means in this direction the reaction is exothermic, and so in the reverse direction it will be endothermic. There's another way of representing this reaction where we do not show heat as a component of the reaction, but we show it as a net change of the heat content of the system separately, where we write the reaction and say that the heat change or enthalpy change is minus so and so. Minus means the system lost this much heat. That is, the process is exothermic. So if we increase the temperature, system will try to decrease. How? By absorbing it. That means absorbing is being done in the endothermic direction, which in this case is the backward direction. So you need to first determine in your process which is the exo and which is the endo direction. Then once you know that increasing temperature, absorption, that is endo direction, and then you refer to your reaction. Endo in this case is backward. If we decrease the temperature, system will try to generate more heat. That is, it will move in that direction where heat is liberated. That happens in the exothermic direction, which in this example is the forward direction. Another example, let's have N2O2 giving 2NO, del H is plus. What does plus mean? That this was there, and the net change in the heat content is positive. Positive means it gained heat. So another way of writing it is this N2 plus O2 giving 2NO minus this much heat. Minus means from surroundings it was minus, and if you transposed this minus 181 to this side, it will become plus. That means N2 plus O2 plus this much heat. That means plus heat means the reactant absorbed this much heat and then gave the product, which indicates that the reaction is endothermic in the forward direction, and therefore in the reverse direction it will be exothermic. This is the key point for temperature factor, that once you have determined your endo and exo direction, then it's the same thing for all reactions. That is, if temperature is increased, system will try to undo the increase in temperature by trying to reduce the temperature by absorbing that extra heat and therefore moving in the endo direction, which in this case is the forward direction. If temperature is decreased, system is going to undo the decrease in temperature by increasing the temperature, that is by liberating heat. That is, liberation means exothermic direction, which in this case is the backward direction. Now let's understand the impact of adding an inert gas to a system at equilibrium. The impact is going to depend on the conditions imposed on the system during the introduction of the inert gas to the equilibrium reaction system. The first one is that adding the inert gas at constant volume. As soon as, for your reference, this is my container which has the gases, and the black dots are indicating introduction of the inert gas. As soon as inert gas is introduced, the number of particles in the reaction system which was or which is at equilibrium increases, and therefore the number of strikes per unit volume on the wall of the container increases. And what is pressure? The number of collisions and the impact of the collisions experienced by the wall of the container is equivalent to the pressure of the gas. If the number of particles increases, the pressure on the walls or the strikes, and therefore the pressure on the walls of the container also increases. But since the inert gas is not going to react either with the reactants or the products which are at equilibrium, their equilibrium is not disturbed, and therefore no effect of adding an inert gas at constant volume, because the number of particles at that constant volume of reactants and products have remained unchanged or have remained undisturbed. Now let's understand the addition of inert gas at constant pressure. This is important. So this is my original system where I have reactants and products. If I introduce an inert gas, these black dots, introduce an inert gas into the container, the pressure will increase. Why? Because the population of the particles in the system has increased. Even inert gases are going to hit the walls of the container. The number of strikes experienced by unit volume or unit area of the container will be, the wall will be more. Pressure will increase. But what is the condition at which we are introducing the inert gas? Maintain the pressure as constant. How will I maintain a constant pressure? If I have lesser strikes or lesser particles colliding per unit volume, per unit time, and therefore I need to increase the volume of the container so that the particles spread out, the density of the particles becomes less, so much so that the number of strikes per unit area of the container is the same as what we wanted it to be to maintain at constant pressure. And for that we have just said that the volume will increase. If the volume increases, then the number of particles per unit volume will decrease. And how will the system try to undo the change? The system will try to undo the change by moving in that direction where the number of moles increases. Now, where is that? That depends on the type of reaction. But what you need to remember, for maintaining a constant pressure on introduction of an inert gas, the volume has to increase. Now, once you know that volume increases, you know that volume will increase, number of moles of reactant products per volume will decrease, and undo change, the system will try to undo this change. How? By increasing moles. That is, the equilibrium shift will take place in this direction. So let's reinforce that with a few examples. So we have this reaction 2NH3 N2 plus 3H2. The constant pressure, we have added inert gas. Equilibrium will shift in that direction where the number of moles increases, which for this case happens to be the forward direction. The equation involved in the contact process, 2SO2 plus O2 gives 2SO3. I have 3 here and 2 here. Because volume increased, number of moles per unit volume decreased. And how will the system try to undo? By moving in that direction where the number of moles increases. Which is that which is that direction? That is in the, where is the number of moles increasing? In the, here 2, here 3, in the backward direction. And let's look at this example. 2 here and 2 here. When the number of moles is the same, backward and forward, no impact, no disturbance. So no impact of change in pressure for such like cases. You get a lot of reasoning questions on this effect of addition of a catalyst to a system at equilibrium. There is no effect on the equilibrium status for a given reaction system on addition of a catalyst. And why is that? That is because a catalyst is affecting the rate of forward as well as the rate of backward reaction equally. Therefore, there is no net change in the concentration of either the reactant or product, because whatever happens, whatever was happening in this direction, the same extent change is happening in the backward direction also. However, because the rates of backward and forward reaction are being affected, though equally, the status of equilibrium will be attained faster or quicker. Like earlier, if it was taking 10 minutes, it may take 7 or 5 or 3, whatever the impact of the catalyst. So a catalyst, very, very important, does not affect the point of equilibrium, but it does help to achieve the equilibrium point faster or quicker. Effect of volume change. Suppose we are increasing or decreasing the volume. We've already studied the effect of volume change in terms of pressure, but let us do it independently. We decrease the volume. If the volume decreases, less space. If this was the volume, now if we make the volume this much, the one in the shaded portion, the number of moles per unit volume will increase. Lesser space, and therefore system will try to decrease, undo. So if moles increase, system will move in that direction, which will decrease the number of moles. Let's increase the volume of the system. So if from here the volume becomes this much more, that means the number of moles per unit volume is decreasing. The system will try to undo that change. What is that undo? Decreased in moles, it will shift equilibrium in that direction, which increases the moles. That again will depend, forward or backward will depend on which type of, what is the nature of your reaction. So questions, let's do some questions based on Le Chatelier's principle so that we know what we can gauge what we've studied. What is the effect of increasing temperature, decreasing pressure, lowering concentration of PCl5, addition of argon? Argon is an inert gas at constant volume to this system, which is indicated in green. So we have PCl5 giving PCl3 plus Cl2 minus heat. Minus heat means from outside heat has been consumed. That means if I transpose this minus here, it will become PCl5 plus heat, which means the process is endothermic. So whenever you are doing, you are trying to understand the impact of temperature, your first step will be to determine the endo and exothermic directions of the reaction. So we have determined that the forward is endothermic. Why? Because this minus heat, that's an easier way of doing it. If this minus heat, if I transposed it here, it will become plus. So PCl5 plus some heat. Plus some heat means it absorbed. So the forward is endo, and we've already said that if in one direction it is endo, in the other direction it will be exothermic. Once this is clear, now easy. Increase in temperature, system will try to undo the change by decreasing temperature. How will it decrease the temperature? By absorbing the extra heat, and absorbing happens in the endothermic direction, and in this case the endothermic direction is the forward direction. So equilibrium shift will happen in the forward direction. Decreasing pressure. How are we understanding decreasing pressure? So if we decrease the, suppose this was the original system, this is your piston and this was the pressure, this gas was contained in this container experiencing. We decrease the pressure means we released the pressure on the system by raising the piston. So the volume increases. If volume increases, number of moles per unit volume decreases. Also direct way what we studied. Whatever happens to the pressure happens to the moles. So if pressure decreased, moles decreased, and what is the system going to do? It is going to move in that direction where the number of moles increase, and that is happening in the forward direction in this example. One second. Sorry. Here. The next was what is the impact of decreasing the concentration of PCl5? The keyword, what is the keyword? Undo the change. So if concentration of PCl5 is decreased, system is going to increase the concentration of PCl5, And where is PCl5 increasing? If the reaction moves in this direction so as to produce more of PCl5. So the reaction system will try to undo the change by increasing PCl5. That will happen in the backward direction. Addition of argon, that is an inert gas, at constant volume. At constant volume, we said that the density or the population per unit volume of the reactants and products is unaffected because the inert gas didn't react either with the reactant moles or the product moles. Hence, no effect on the equilibrium because the number of reactant and product moles remains unchanged. Do the number of moles of reaction products increase, decrease, or remain unchanged when the following equilibrium is subjected to decrease in pressure by increasing volume? So, whether you are talking in terms of volume or whether in terms of pressure, both are related to one another in terms of inverse connection. So, we have the reaction CaO solid plus CO2 gaseous gives CaCO3 solid. This is our reaction, and for this we are asking that will the number of moles increase or decrease, moles of the reactant products increase. That means he's being specific. He's asking you whether this side is going to increase or not. So I have the reaction once more for you. CaO solid gives CO2 gas, reversible, CaCO3 solid, and the question was, if pressure is decreased by increasing the volume, what will happen to the number of moles of the products? So this was my container. This was the original pressure. We have decreased the pressure. As soon as the pressure decreases, even if it was not stated that the volume is increased, the volume will increase. Or if the volume will increase, obviously the pressure will decrease. So pressure decreased, volume increased. Whatever happens to the pressure, the same happens to the number of moles, and the system will try to undo this change. How will it undo? By trying to increase the number of moles. But you will also remember that only when we are talking of these factors, we are talking only of gaseous components. So the equilibrium will shift in that direction where the number of moles of gaseous components will increase. Pressure decreased, moles decrease. System will undo the change by increasing pressure. That will happen by increasing moles. And where is the number of moles increasing for gaseous components? Here you have only a solid. So the gaseous moles are being formed in this direction. That is, equilibrium is being favored in backward direction. That means he didn't ask us in which direction. He's asking us, will the product moles increase or decrease? So because the equilibrium shifts in this direction, obviously the product moles will decrease. Another example to understand this, 3Fe plus 4H. Please, I've highlighted the important part. 3Fe solid plus 4H2 gaseous gives Fe3O4 solid plus 4H2O gaseous. If same question, you have to tell whether the moles of product reactants will increase or products will increase or decrease if we decrease pressure by increasing volume. Same thing. Volume is increased. If volume is increased, then obviously the pressure became less. The story is the same. If pressure is decreased, system moles will decrease and the system will try to increase the moles. But one thing you have to remember here, take a look at, just like here we said, only the gaseous components are to be considered. Here also 4 gaseous components here, 4 gaseous components here. So this whole story is null and void here, because as soon as the number of moles of gaseous products is equal to the number of moles of gaseous reactants, there is no impact of changing pressure on such a system. Using LCP, that's just a shortened version I have given for Le Chatelier principle. Using LCP, predict the conditions of temperature and pressure which would give high yield of the products. So this is the application of the Le Chatelier's principle, where you are not being asked will it move in forward or will it move in backward. He's simply asking you that what conditions of temperature and pressure will aid the formation of the product. Like this is the contact process. So let's decide whether our reaction is exo or endo. So the net heat change of the system is minus. Minus means loss, and loss means liberation of heat, and liberation of heat implies that this reaction is exothermic in the forward direction and endothermic in the backward direction. So we want to move forward. Exo, that means it is producing more heat. So it is producing heat. So if we lowered the temperature, the system will try to undo the change. How will it undo? By increasing the temperature. Increasing the temperature means by producing heat, and producing heat means moving in the direction which is exothermic, that is the forward direction. High pressure. If we increase the pressure on this system, directly whatever happens to pressure, same thing happens to moles. Moles will increase. System will try to undo the increase in moles by moving in that direction where moles are decreasing. So here you had 3 moles, here you had 2 moles. System will move in that direction where number of moles decreases, which is the forward direction. So this is an application of LCP helping you to understand how to improve the concentration of the product concerned. And you can test yourself for this Haber's process. N2 gaseous plus 3H2 gaseous, 2NH3, del H is given as minus some value of kilojoules. Identify the conditions of temperature and pressure which would allow us to improve the yield of ammonia. That's it for this class. As I always say, please repeat, revise, reinforce. One reading will never clear everything in one go. So revision is always good and important. Work hard. God bless.